Hello, everybody. We're back on this Thursday for the second stream of working on a very simple x86 instruction decoder in C. I was doing some prep work before the stream just now. I was reading up on some stuff that is not particularly interesting to watch on stream, although I'm going to be going through it, some of it on stream, but just not the like reading paragraphs and paragraphs of text. But what I came across, or what I ended up at while going through the Intel manual that I was looking at briefly on the previous stream, is this table at the very end in Appendix B. After machine instruction format, there's this general purpose instruction formats and encodings for non-64-bit modes, which is exactly what I need for what I am working on right now in the instruction decoder. It gives each instruction and what the encoding is as bits in a relatively easy to understand way. There's a few sort of variables that are in there. So in the case of this instruction, the lowest valued bit in that first byte of the instruction determines which registers are being referenced by this, which is effectively the mod RM byte. And it's using the mod. I say mod, but I think it probably should be pronounced mode because it's talking about addressing modes. So it's using the addressing mode 3, which means that this is a register, and then also because of the mechanism just for this particular opcode specification, the middle piece is also a register, which is not always the case. As we can see down here, we've got the same 1-1 that then identifies the low 3 bits of the mod RM byte as a register, but the middle 3 bits, or bits 3 through 5, are fixed at 010. This is what they call like an opcode extension. So it's additional bits that help identify what opcode we're talking about, because presumably this pattern exists somewhere else, but these 3 bits are different. And in fact, I think we can see it right here. Keep selecting everything. So it's the same pattern for add versus add with carry, except we've got 000 here and 010 for the add with carry version. So that's, all of this stuff is relatively understandable to me right now, which is good, because I think this is the resource I'm going to use for going forward with the code that I've been working on. I was looking at DataDesk. Throw up Emacs. I want the makefile. Okay, so we can keep hammering away at some of these 1-byte opcodes. I'm going to skip the ones that have any sort of mod RM byte, or follow that up with immediate data or displacement, or that have the SIB byte, which I don't know that I have seen any of those thus far while looking through. It's probable that I just am not identifying it properly, but it would follow mod RM, which is this one, So we would have that, and then we would have another to indicate the scale index in base. But I don't see it right now. I don't see any instructions that have that in the encoding. Oh, you know what it is? Oh, right, because a certain value for mod, I think, or it's something in particular within the mod RM byte, sort of determines whether you have SIB or not. So it's only in the 32-bit addressing mode, and it is when you have RM as 100, I guess. So, okay. Then, yeah. So if we just have the low 3 bits are 4, then that means we're going to follow it up with an SIB. But in any case, I'm not actually going to be working through those. At least not, that's not what I'm going to tackle immediately. I'm going to continue on with as many of the single byte opcodes as possible. But I want to point out some weirdnesses that I noticed that will make the code less elegant than it normally would be. So one thing that is mentioned in the sort of chapter 2 where they describe this stuff in just, more I was going to say narratively, but like it's just a written description rather than a table of all the details for each instruction. But they talk about how 2 or 3 opcode, 2 or 3 byte opcodes are encoded, and we can see them here, or at least the 2 byte ones. Oh no, this is a 3 byte one. So they always start with 0F as the first byte. That is what they say. But then we have a couple of these outliers up here for instructions that I can only assume are just no longer relevant to what a compiler is going to output. Like maybe you would use these if you're hand coding assembly back in the 1980s, in the early days of x86. But these are 2 byte instructions, and the leading byte is not 0F. So I don't know, gonna have to deal with those specially, and find out how similar these are to other instructions that might be single byte instructions. And that is an annoyance that I am not sure yet how I want to deal with it. The fact that this table, as nice as it is, and I appreciate that I have access, that it's presented, because it's going to be a critical resource. It is organized by alphabetical of the operation mnemonic, the opcode mnemonic, I guess. So in that manner, if I want to find out, hey, is there anything that is like 11010111, like is almost the same as these two, but has a 1 in the second to lowest bit, I'm gonna have to like scroll through all of this stuff to see if I can find any that match that, because that might make it harder for me to easily write some code that is very clear in its manner of detecting this stuff. So basically, at some point I would like to pull this out and get it into a table that I can sort by, sort by the actual bits of the instructions. So I can see all the instructions that start with a nibble of 001, for example. Are they all add with carry, except for the one-offs that have immediate data and are encoded differently? So are they is 0001 only used for add with carry? Probably not. But it is a bit difficult to be certain on that just because there's a lot of them in this table, and I think it would be easy for me to miss stuff. And it's certainly kind of tedious to do this manual browsing through to find out. For example, these are some other weird ones that are going to come into play and be a difficult challenge, let's say. I'll get to that in a second, but yeah. So there's definitely some degree of annoyance in how this is organized, and I would like to sort it at some point, but I'm not going to do that on stream. I think it's because of the way that it's presented. It's also going to be kind of annoying to come up with a bit of code that transforms and sorts it. I guess I could look at this website and see if he has also, yeah, see, I don't think, because this is there's a couple different websites, and I don't remember the rest of them off the top of my head, but there's a couple websites that take this PDF and, as I say, mechanically separate it into distinct files using a script. So, it's helpful if you are looking for a particular instruction. You're not looking for the encoding exactly. I mean, like, you can get the encoding here, but it is not, it's not represented in the way that is most helpful to me, basically, unlike this table at the end in the appendix. So I can look around, see if anybody else has actually taken the time to parse this out and convert it into a nice table. But yeah, mostly I would prefer if I could sort it. So let me get to the other weird thing that I noticed that's going to be perhaps annoying. And then I'm going to talk about my strategy, how I want to potentially update the code that I have right now before continuing on to add more of these 1-byte operations. Yeah, stuff like this. The push and pop are annoying because they encode the segment register directly into the middle of the byte. It's a 2-bit register, or 2-bit field, basically, within the opcode. So it doesn't support particularly many, and it can't support CS, which is encoded as 01, because that would make it 000011111, which is the same as the multi-byte prefix. Although it's interesting, CS cannot be SREG2 in this usage, but you'd think it could be in the SREG3 setup. I don't know why it doesn't allow for that, I guess, but basically what this means is, let's say I want to approach this by like switching based on the high value nibble from the first byte of the potential instruction. And we're not considering prefixes, again, still not getting to that part. But if I want to look at the first 4 bytes, or first 4 bits rather, it would be nice and convenient to be able to say, oh, if it's 0, maybe that means that we're in a 2-byte opcode or 2 or 3-byte opcode situation. Let's look at the low nibble. If it's an F, then we go. And that is actually true, but in order for, like, basically this same instruction, if we are looking at the first nibble, is going to be 0000 or 0001. And technically those both could be a pop instruction depending on what the low 4 bits are. So basically there's not a lot in this setup that is amenable to a very straightforward parsing of the first byte into something that I want to use. But I still think I'm going to go with, let me parse the first nibble, the high nibble from the first byte, and then start switching on that, and it'll just, we're going to have some complication. But either there are some more elegant approaches, and maybe I can figure those out after having done it in a less elegant way. Maybe those will become more clear to me, or there really isn't any good way to do it, and you just go with what you can, or what, the approach that you come up with. So previously I was looking at the upper 5 bits, and that mostly works. There's like one instruction where I don't know where in here it is, but I'm already into the 64-bit. There was one that had a S reg. I think it might have been W reg, but it used this bit as a flag, basically, as a field within the opcode, as well as the low 3 bits for the register, meaning that it might not be as ideal to look at all the top 5 bits. I don't know. Maybe I should still look at the 5 bits. Because if I look at the 5 bits, that will definitely include the SRAG2 for the pop and push, which have segment register encodings. And that's confusing. Where do we have... So we have pop for pop a word from the stack. That makes sense, right? Pop something into EAX, let's say. Or, well, if it's popping a word, then I guess it's popping into AX or something. But we don't have push a single register onto the stack. This I don't understand. Oh, sorry, it's just push operand on this. I'm like poorly reading this. Okay, so we have FF, and then these are the 3 bits for the opcode extension stuff, I guess. Okay. But again, all of those are to come later. So I think I'm going to start with, let's look at the top 4 bits. And we'll call this opcode H for high. So this is the high nibble. I guess technically it needs to be, yeah. So let's fix the existing ones that we have right now. Let's go to the, oh, I don't want that. I want this. And so yeah, we want 1001. Okay, so for this we have potentially 16 cases, right? Oh, that was that one. Okay. Just gonna sort these according to the bits. So I want to just make sure that I cover all of the possible values for the high nibble. What is going on here? Okay. All right. And then what I'm going to do is, I guess, put what should it really? Okay, fine. So at least I'm going to put comments to say what bytes these might be, or what opcodes might come with this high nibble. So we can start with if we have, or I'm sorry, it's 0F, not F0. Okay, so if the first byte, or the first, the high nibble that we're looking at is all zeros, then it could be a 2 or 3 byte opcode with the 0F prefix. What else could it be? And this is going to get tedious very quickly, but that's what I'm in for, I guess. Could be an add. This is stuff that I was just looking through. Yeah. Could be an or. We do it this way. Oop. God Okay. Skipping all the ones that are the prefix. That's weird that they would write. That's just a typographical error, I guess. F's instead of ones. But it's an undefined instruction anyway. That's interesting. Doesn't matter. Okay. And yeah, so that's it. Those are all the ones, all the instructions that you might have, unless in 32-bit mode, let's say, 16 or 32-bit, I guess, legacy mode, if you have the high nibble is 0. So fewer instructions than I anticipated, actually. And that's fine. And, you know, it might be that there are prefixes include that, although I thought the prefixes were like F2 and 3 and 66 and 67. Okay, so let's move on to 01. Right, that's going to be add with carry. And SBB. And then this is 64-bit. Okay. So just 2 for that one. This could be an and. I guess let me just search through everything first, and then we'll get to typing them in the comments. Could be an and, could be DAA or DAS. You know what? Since I'm not going to remember that. Okay. Could be sub. And could be some prefix bytes. Okay. Why would that be prefixes? Which prefix? Oh, segment override prefixes? In here somewhere. Chapter 1. Right. 2E. Yeah. Okay. And 2.6. So what is it? CS and ES? Okay. But again, we're not going to handle those for a while probably. It's just nice to have the comment in there. Let me double check that that lines up with what they specified. CS and ES. Okay. Cool. Then we're looking at 3, which could be AAA, AAS. Nope. Okay, can't use the keyboard. Compare. XOR. Okay, and then segment override for DS and SS. Okay, then what do we have for 4? Could be a decrement. Okay. Put the alternate on there just in case that's helpful. Do wonder if those get a lot of use. Okay, that's all the ones for 4. Oops, not that one. There we go. Five could be pop alternate, as well as presumably push alternate. Yeah. Okay. Honestly, I don't know. This is going maybe a little bit better than I anticipated. And ARPL 4.6. Oops. IML, as well as INS from DXport. I've only ever really seen IN, I think, not INS, but it doesn't matter. As well as invalidate process context identifier. Okay. Inv PCID. Outs. Pop-A-D. Okay. As well as push AD. And just straight up push. Interesting. Okay. And then some prefix bytes. Which is the FSGS. Okay, lots of stuff for 6. Popular, high nibble. What about 7? Jump, of course. Or at least JCC condition. Is that it? Seems like it. not very popular to have 7 as the high nibble. What about 8? All right, so it could be ADC. Could be add immediate. And immediate. Sensing a theme here, they added the immediate versions of these and encoded them all with 8 as the high nibble. LEA and some moves. Moving for segment registers or immediate pop. Just pop. Okay. And then SBB immediate. As well as sub immediate. Test. Just test, I guess. Don't have any other easy way of indicating that. As well as exchange, which is interesting because, oh, I see. Yeah, this is the next one that we'll get to. Okay. And then XOR immediate. Right. And what about 9? We've got a call. CBW and CDQ. Yeah, I think I listed those up here, right? Yeah. So CBW / CWD. And CDW? No, CWD, right? Yeah. Okay. Yep. LAHF. Okay. NOP. So yeah, they do bother to list it separately. I guess it, makes sense. Sorry, am I missing something here? Yeah. Okay, pop F / pop FD. Push F and push FD, presumably. Yep. SAHF. and wait, and then exchange. I already listed that earlier. Okay, cool. 10 or A, I guess I should say, is CMPS, CMPS B, W, and D. And bloods. Move just for EAX, both to from. Move string operations. And scan string operations. So there's definitely more pattern in store string operations than I think it was obvious to me at the beginning. Just, I mean, obviously several of these have similar categories of operations, all when you have the same high nibble. So that makes me feel more confident that doing it based on the high nibble is maybe more appropriate. Because yeah, if it starts with if the high nibble is A, then that's how we encode all of the string specific opcode stuff: compare, load, store, move, scan. So that's nice. I mean, just from the standpoint of like, it feels like the outcome is going to be a little more organized from that. All right, and then B. We're going to get through these pretty soon. Right, okay. I can just call that alternate, because it's a particular alternate encoding, I guess. That was all of the ones for B. Interesting. Basically nothing starts with a B. Okay. What about a C? Yeah, we got several. Right, the interrupts. And then into int O, I guess. iret and iretd. Okay. Interrupt 4 on overflow. Yeah, in O, I guess, rather than into. LDS. Leave. LES. Immediate. Sorry. RCL immediate and RCR immediate. As well as ret. All of the ret. Yeah. And ROL immediate. And the shifting, but not right. Of course, you don't have where is that? It's down here probably. Okay. And SHL immediate. All right. And then D. So close. AAD and AAM. Those weird ones. Regular RCL, RCR. I guess SHL and SHR, yeah. And then XLAT and XLAT B. Okay. E. Why is it highlighting differently now? Whatever. Oh, I guess it's because it's the first one, maybe. So it's call. Whereas the previous calls, no, we just haven't gotten there because those are F. We were on. Can we distinguish these in some way? I'm not going to worry about it for right now. And then in. These ones are down. Okay. Just regular jump. And I'll list that the same. Loop and then the conditional loops goes out. Yep. Okay, and then F finally. So indirect calls. Okay, whatever those ones are. Presumably deck and ink, although don't put ink because there's going to be a bunch in the middle. Div. And idiv. Oh, and halt. Okay. As well as some of the imul stuff. Imul for EAX in particular. And ink. And then jump indirect. And lock. And then just null and neg. Negate. And not. And then push. And could be rep/rep ne. STC, STD, STI for setting flags. Tests for immediate versions. Some of the immediate. Yeah, just so I'm trying to, like, when I write down okay. Interesting that the prefix bytes doesn't include the rep stuff, even though they are listed as a group of prefix bytes. So, for example, looking at test, right, there are 3 different high nibbles that all could encode a test instruction. And it would be nice to say, oh, if the high nibble is F, then that means it's a test instruction. It could be a test instruction with immediate data. But this one is also a test instruction with immediate data. But I could say this one is testing EAX with immediate data, I guess. and that one is 10. Oh, I do have it there. Okay, cool. So this should be all the instructions, broadly speaking. It'll be all the single byte instructions because I just have a one line comment that covers all of the 2 and 3 byte opcodes. Again, not including any 64-bit stuff. But it does mention, which high nibbles might be indicating a prefix byte. So that'll come into play later. So what do we want to do then? We could fix these existing ones that we have. So if we say we also just get opcode low, because we're going to need that for everything else. Like each of these cases is going to have one of those, I guess. And this is a incredibly ugly way to go about it right now, just in one giant switch case, and then looking at doing additional switch cases for each of these. Might just organize it a little better. So let's do what's the first one that I had? It was 6. Okay, so what I'm going to do is define other instructions, or sorry, other functions that will handle the case for each of these 16 possibilities for the high nibble. So this is the one where the high nibble is 6, and we'll pass in what the low nibble is. Then we'll pass in the instruction stream moved beyond the opcode that we just parsed out, basically, and as well as our pointer to the instruction where we'll store the ultimate instruction data. So then I guess we could move this up here. And this is like, it's not going to work once we get into prefix bytes and stuff, because I don't want to go into here and then have to call into something else that has to parse out opcode bytes again. We'll call this opcode 6x, let's say. So this is the function to call when we know that we're decoding opcode bytes, rather than prefix bytes or something following the opcode like mod rm, sib, etc. Because if I'm in the prefix, I want to be parsing those prefixes before I go into the logic about opcodes. I don't want to go into this function and then have to like somehow organize the code to be able to go back and maybe recursively call this opcode bit. Because I don't know if there was a address size or an operand size prefix on an imul operation opcode, then this would be recursive call, which is not a bad thing. It's not going to recurse infinitely, obviously, but like it just doesn't feel like the right flow. So realistically, the decode function will, when we get to prefix bytes, have to parse out the prefix bytes first. Once it has figured all of those out, then we'll go in to the opcode switch and call into one of these opcode decoder functions to finish the work. Because right now this is like, I'm just going to move this bit into here because it's more for organizational purposes than anything related to control flow. Because we're going to do another switch for opcode L right in here. And so if we're looking at 6, could be these prefixes, but mostly we could see if it is, oh, I missed bound. So if the low nibble, that, and that has the mod RM. So I'm not going to implement these just yet. And then, yeah, we got the imul, which is 1, 0. So let's go ahead and throw these on as comments. Pretty sure that was the right order. Right, bound is 1, 0, yeah. Okay, then also got for imul 1, 0, 1, 1, and 1, 0, 0, 1. And 1, 1, 0. This one is INS. Why do you want to do like this? So same process, where we sort of, now we're looking at the low nibble and try to figure out, is there a particular instruction we can work out from this? And I'm putting breaks in here, but realistically they should be like abort until I have the logic for decoding them properly. And oh, this is another one of these oddball ones where this is a 4-byte opcode, since we're not counting the mod RM as part of the opcode, like byte length. And this is an extreme oddball because the multi-byte opcodes were mentioned to always start with this back in chapter 2, and they've never mentioned to my recollection, like in the chapter 2 section, they never talked about a 4-byte opcode. So this one is new to me, let's say. I hadn't even like, I was looking at just this bit when I was adding it in the list earlier. I didn't even bother to see that this is already like, I guess this is a prefix. Oh, this is a 3-byte opcode with the like first byte specifier that it's a multi-byte opcode, and there's simply a required prefix of 66. So I'm going to take that one out because that doesn't really count according to the logic that I'm going on. I don't remember which kind of prefix is the 66. Operand size prefix. Okay. But yeah, it says it's also a mandatory prefix for some instructions, so that's how they're deciding to represent it in here, is just that's how you encode that particular instruction. It has that prefix as the first byte. Well, that's fine. But I think for our logic, we'll need to parse it out as the prefix byte before we can determine that it is this particular instruction. Anything else? Yeah, outs is 111, and then the others. Okay. Then pop A and pop AD. Should I be doing this? I'm going to keep with the order it in terms of the value of the nibble rather than the alphabetical sorting of the mnemonic. Okay, and then we also have a push. Let's make sure that my sorting here is reasonable. I think so for now. And that is 1 0. Interesting. Okay, so we can't quite hold to an exact sorting. Because of the way that they're sort of interleaved, right? So like this one technically comes up here, but these are both imul. So for the purposes of having the fall through and being able to not have to duplicate the code because I've put it into 2 separate case switch statement cases, I'm going to go ahead and break the sorting a little bit and let that be what it is, because the difference between these two is just in the lowest bit, but they have a varying second to lowest bit. Okay. And that's probably everything, just because it's like, how much more can you put into this space? Okay. So we have push A and push AD, and then also, okay, so let's copy our code from down here. And I guess in this case, I don't, yeah, I'll fix it in a second. I guess that's what I can do. Keep it simplified here. just abort in all of those cases. Okay, you know what I'll do here? Say return -1. I meant to be a little clearer. And that'll be our indicator to whoever calls the decode function that they have called, that we have failed to decode the instruction. Why is it like that? Okay, so when we call our specialized function for decoding opcodes that start with the first byte having a nibble of 6, we'll pass in the low nibble, and we will pass in the instruction but +1, moved forward 1 byte, and then the instruction stream rather, and then we'll pass in the instruction object itself so that we can modify it as necessary. I feel like that works. And down here, rather than abort, we're gonna say return -1. So we could do just, let's keep with. I realize I'm like working on changes that aren't that important. Just yak shaving or whatever. Okay, so we'll keep it the standard of just saying break between all of these. And if we get out of the switch without having returned something, then we'll return -1 as our default to indicate failure to decode. And honestly, returning 0 should be, maybe that's what we need to do instead, because, I mean, I don't know. If you decode something and it says the instruction size is 0, I'm not sure what has happened there. That means there was no instruction, I guess. Let's see. Yeah, we'll just do a generic message rather than give details for right now. You know what? Let's do is that it for a single byte? Actually, we have standard lib, right? So we could do like be slightly more standards compliant. Let me double check that. The old table. Oh, I should be looking at the C one, I suppose. But I think it'll be the same here. So do X, HHX, yeah, that's fine. Okay. Then we will because for right now it's a single byte instruction, but could be multi-byte in the future. Then just return 0 here and up here as well. Okay, now we can also do this guy, which is 9. I guess that's just T code L const. And put that in there somewhere. Don't even bother with this. Yeah, no, I don't use it right now. No, we're going to repeat the same thing that we did before, which is to only include the ones that we actually know that we have. Okay. So the first one was call as then we've got these two, which are the same as these two. Actually, let me put the comments on these. So it's CBW and CWDE. Yeah. And then CWD, CDQ. Okay. Looks fine to me. So we had LHF and NOP, which is 0. Yeah, this is okay. Because then we've got, well, let's deal with that in a bit. What does the push look like? These don't have any other. It's kind of arbitrary where I am drawing a distinction to include two instructions together, but these ones I think go together in the same way that these do. But again, that's very arbitrary. They're related instructions, but whether you should combine them logically in that way, I don't know. What do we got? SHF. Yeah. See, like, combining these two makes more sense to me, I would say. We go up to IML. Where we have, right, because these are absolutely two versions of the exact same instruction with the S bit being a 0 or a 1. So these two make sense to group together. These are technically different instructions. They just only differ in that low bit. And that pattern shows up in a few places where you've got these sort of paired push and pop, store and load kind of pairings. So I don't know. It's much more arbitrary what I'm doing right now with those ones. And let's see. Is that everything? No. And weight as well. Again, the exchange. Which I can see why there's good reason to maybe count it as a NOP. And like actually, so what I was saying on the last stream where I was like, you know what, maybe I should just count it as an exchange EAX, and let somebody else deal with it. I'm going to stick with that because I think that simplifies things a little bit in the data structure that I'm outputting. If I can treat it like a slightly different version of the other exchange instructions. Granted, that's a pretty arbitrary decision. There are definitely some use cases where that might be pointless. And Permikov, thanks for coming by again. I mean, it's slow for sure, but I'm getting a more comprehensive view of what I need to be doing, and in going through that, I'm getting a better sense of the patterns in the encoding, as well as the cases that really break those patterns. But yeah, seeing some of the patterns and definitely seeing having this table here in the appendix B in the manual is very helpful because it's calling out which ones have the register or have a width specifier bit or a sign specifier bit. Or I guess this is like sign extend on the immediate data operand. I believe that's what the S is about. Yeah, I think it's only on those. Well, yeah, I doubt it'll make perfect sense, but I think some of the things that I've already started to notice, where there are the like, if we take a look at this SBB instruction, we've got the same high nibble for the first byte of the instruction for all of the cases except for these two, which take a register or a memory address and an immediate operand. There is a case where they have an immediate and it is forced to be EAX or AX or whatever, and that follows the original pattern. But we've got these two oddballs that have a different high nibble. Well, we see that as well in some other ones like OR. Same kind of thing. OR is all zeros for the high nibble, except for these two cases. And it turns out the situations where there are instructions that have these additional two cases that are encoded somewhat differently from the rest of them, it's always an 8 in the high nibble. So it's like, my thinking is at some point they added this to the instruction set. Probably was not in the original 8086 instruction set. Is purely my guess, and they use the additional 3 bits from mod RM as a way of extending the opcode bits. What bits indicate what opcode we're talking about. So yeah, like some of those things start to be more obvious as I go through this structure and organize it according to the bitwise encoding, or in a way that makes sense for me right now. But I'm sure that other stuff is just never going to make sense. Like most particularly these ones up here, where this is what is that? D is the first one. Like that's not part of a prefix byte, and it's not the designated leading byte of a multi-byte opcode, but it is a multi-byte opcode. So like, what's up with that? Why is that a thing? These might just be the few, because there's really only these two that I saw in this sort of category of total oddballs. The only other stuff that I saw that really is going to be annoying is the ones where they encode the segment register in the middle of the first byte of the instruction. Down here somewhere, like push. Yeah. So like these ones are going to be a little bit annoying. Only a little bit, but it's how it goes. So I still think my approach of like, let me pull out the first nibble, sort based on that, and then each thing will deal with the potential instructions that could come out of it. I don't know. There's going to be some duplication. So I guess the broad way to state what I am trying to achieve and what I think is very difficult to achieve because of the manner in which the encoding has been done is writing a decoder which has as little code duplication as possible. So what is the principle? Like dry, right? Don't repeat yourself. Don't have the same logic specified in a couple different places for general software development purposes, because if you have to change that logic for whatever reason, then you have to change it in multiple places, and you're just opening yourself up to the possibility of failing to do that and resulting bugs that may be harder to catch depending on your testing regime, let's say. But there's not, maybe if I go through all of this and then do a nice code review and plan out some refactoring, there might be a way to achieve this where each instruction only has the logic for building that instruction data structure, the like output data structure, only happens in one location. I could sort of trivially achieve that by putting each instruction into its own function, and that function just like initializes the instruction data structure. I realize I'm like saying instruction structure a lot, but like rather than have this bit of code that just throws the opcode into the inster object or struct in this case, I could write a little function that's like make pop-ad, right? And then it says inster opcode equals pop-ad. And then I could do another one, and we could just do something like that, right? But that is, and that would be a trivial way to get to the point where I'm not repeating this line of code anywhere. But then I'm repeating calls to that line of code several places. It's still better, but it's not a lot better. And it's like, it's not reducing the complication from the standpoint, or it's not reducing the repetition that goes to the idea of how complicated it is to follow this logic. It is reducing the code from the standpoint of if I had to change how the push AD instruction was built, how that output data structure is built, I would only have one place to change it. And to that extent, maybe it's worth doing. I'm not going to do it right now because the data structure is so simple, but it might come to the point where I want to do that as I start to have like parse out mod RM and SIB and displacement and all of that stuff. Because I'll need to expand the data structure to be able to track all of those things. And yeah, it's just, but at the same time, right? Like, let's say these two were actually instructions that had a mod RM that could have an SIB and an immediate. So both of these. Then if I write the code in there that does the parsing of that stuff, I'm going to have to repeat that parsing code in both of these basically, unless I can make it a little more generic. All in all, it's just, it's not easy to go from the bits to exactly what instruction you have without doing like the world's worst switch statement, which is probably a lot closer to how it actually works in the hardware. You'd still need stages for prefix bytes and stuff, but let's say that where you're at right now is 1 to 3 bytes of an opcode. You could definitely have a switch statement that had 65,000 times 256, whatever that is. I don't know what 3 bytes worth of combinations is. But you can have that many cases in your switch statement, right? And then each one of those represents one possible instruction in all its potential detail, not including the remainder bits that you'd have to still parse out for the following bytes after the opcode part. But like right now, I've got an add here and an add down here, and move shows up in a few different locations based on the high nibble, right? So there are different code paths that'll take us to different ways of parsing out a move instruction, stuff like that. So I don't know. It's gonna be messy no matter what, I think, is the end result. Which I was aware of on the last stream, but maybe not as clearly. I didn't have as direct of a sense of how it was going to be messy. Now I'm getting a better sense of exactly how it's going to be messy, which is fine. So I'm not going to have these functions for now. I'm going to leave these comments, I guess. It's not really appropriate to have them here. I can put them up here. Oh, the other thing that I saw was, there's no prefixes for this yet. Okay. What was the other thing I saw? The prefix bytes can be in any order. The traditional prefix bytes, at least. All of those come before the Rex prefix for 64-bit. Oy. Wow. Okay. But in that setup, they can still be wherever the fuck, in what order. I shouldn't be cursing, which is kind of annoying. That's a decision that I would be very surprised if I actually ended up understanding why that was the case. Oops. Okay, so at some point we'll parse out the prefix bytes, but I'm not going to get into that for now. We still have quite a bit of time for this stream, so I'm trying to think what stuff I should start working on. I don't think it's particularly interesting to work on more of these single byte instructions. That's what I should be. So right now I've got a couple of the single byte instructions working, but maybe I should work on some of the single byte opcodes that are multi-byte instructions because they have mod RM. Just as a like varying things up rather than spending all of my time on the stream going through, okay, let's implement the exact same kind of behavior for AAS or whatever it is. Like, yeah, AAS and AAA would be extremely similar to the code that we currently have. We just parse out the low nibble. If it's exactly this, or it's exactly this, then we make that instruction. Not terribly interesting. So maybe we should push ourselves a little bit. Don't forget the showbiz part of the stream. Yeah, I mean, I don't know how to make this interesting, to be honest. If you have any ideas of how to make this interesting, let me know. Because there's just a lot of tediousness in here. And I'm not some superstar programmer like Gamozo, who's, just coding at 100 miles an hour for 12 hours in a row, which I guess would be 1,200 miles of coding. Yeah, it's going to be me trying to think over how I'm going to do this and staring at some documentation and then typing little bits. It's going to be a slow process, I imagine. So, but at least, I can try to vary up what I am working on in the code. So I should pick a reasonable instruction. I mean, maybe the first one to go for is like just something with immediate data that doesn't even have mod RM. Guess. So let's do an and, this immediate and that, or it ands EAX with an immediate value. And I could potentially then, repeat that behavior for add as well, and war and a few other ones. But it's like, I don't know, maybe that becomes the right way to factor it. I'm not going to try to switch stuff up for that right now, but it might be, okay, we've got certain categories of instructions, add with carry, add, and, or, XOR, that follow this pattern. They have a different high nibble, but then it looks like the low nibble is always the same. And yeah, I mean, that's one, that's closer to how they conceived of, or at least like, I don't know, it feels more like an intentional structuring. And that would cut down a little bit on the logic, because then we're doing the same parsing kind of behavior for each of those once we've determined which. The more I talk about it, the more I'm convincing myself that it's the way to do it, but at the same time, it's going to be like, hey, just rip out a bunch of the code that you just wrote. But that's fine. So what do we say 0 includes? Add and or in the 2 and 3 byte opcodes. So we could do that. Is SBB the same? I think it is. I'm trying to see whether we can easily... Yeah, SBB works the same way. So for these first two cases, with the exception of the multi-byte opcode prefix byte, which I can easily just special case and say, hey, if the low nibble is FF, then go a different route. Other than that, all of the instructions that are encoded with one of these as the high nibble have that same pattern to how the low nibble and possibly additional bits in the mod RM byte encode which instruction it is. Don't know if that's the case for this one as well. Let's look at sub. Yeah, sub follows that pattern. I think maybe test not quite because it doesn't have all of the varieties. And its immediate ones are a different starter. So we had sub, and what is DAA and DAS? Those are like single byte ones, I think. Right? Yeah. Okay. So for these first four, there's ultimately like 3 categories of behavior for how we would want to parse the instruction. It's either a multi-byte opcode, in which case we have to go and do a second layer because there's a lot more opcodes that could be hidden behind this first byte. Or it's DAA, DAS, AAA, AAS, which are both single byte opcodes, or single byte instructions rather, and we can probably special case those right away as well. And then the remainder of the cases, the remainder of the opcodes are all the majority of the particular variants for that, whatever that opcode is. So like it's 4 out of 6 or 6 out of 8, whatever it is. 5 out of 7 compare varieties. Yeah. All but these one-off immediate ones. So maybe that's the way to factor it, is to take these 3, see if I'm missing any, and consider them to be a single case where it's just the opcode like name, conceptually at least, because again, I'm not really storing the name, I'm not storing the mnemonic for the opcode, and I did want to have a unique identifier for each variety of the opcode, but I think I'll set that aside for now. But they would all go down the same code path because the behavior of figuring out which variety of that operation we are dealing with and then parsing out the operands for it are all going to be the same logic, as well as keeping the cases where we've got an immediate we need to find or as well, because we've got add, ADC, and compare. Oh no, or is in there. Let me make sure. And then XOR. So we got XOR, we got compare, sub, SBB, or, and ADC. Yeah, okay. So, and all of those are comprised in here with the immediate cases in here. So can I reorganize things to have that code path parsing? Well, I'm gonna give it a shot, I guess. Let me say like if opcode L is that, then we'll just break. We don't know how to parse out multi-byte opcodes yet. So we're looking at, let's look at DAA. And we have F or 7 on any of these, like add. I don't think so, actually. Sub and SBB. Let's compare. Interesting. We might be able to get away with that. So what I'm thinking about is move as its whole own. We're gonna deal with that separately. None of these. Yeah. So the low D word, or sorry, the low nibble of the byte for all of these instructions that I've been talking about, add or ADC, SBB, etc., none of them have the same low D word as DAA, DAS. What about AAA and AAS? No. So, because these are either 7 or F, and none of those other ones had 7 or F as the low nibble. Which means I think I could actually take out these breaks. Okay, so all three of these cases will flow down to here if we don't hit one of those other comparisons. Seems okay to me. It's probably a questionable choice, but I think it would work. We're going to find out eventually, because I would need test cases that include DAA, DAS before I could actually see that. So how do I want to, what is a good name to group this set of instructions? Sort of like whatever. Yeah, so I mean, we've got, you know, basic arithmetic, binary integer arithmetic, but not multiply and divide, as well as basic bitwise logic operations. Let's call it this for whatever reason. I guess I may have made this more difficult because do we want to take advantage of the fact that we've already parsed out the high nibble in trying to then determine what the opcode is? Or do we want to do that in the function that we're calling? Let me go back to before I had pulled everything out. Okay, so add and or have the same high nibble. So it's really, it's going to be this high bit is 1 for or, I think. Yeah. Okay. Looking at how these compare. I have a 1 here for or. Okay. So it's going to be Why does add get highlighted like that? I don't know. Maybe I should prefix all of those things with op. Except for down here. What am I doing? Just constant yak shaving as I code stuff. Okay, CWD. What did I change there? Of course. Whatever. Okay. So but then yeah, that means I cannot take advantage of the fall through without making the code clear. So I'm just gonna not deal with it later. Then I think it's probably the same thing here. Let's double check. ADC, 0 in the ones. SBB, ones in that high bit. Okay. And where did the other one go? Okay. So now we want to look at compare an XOR XOR is the one with the zeros. And in sub has the 1 for sub. SBB has the 1. Okay. I put it wrong here as well. Great. Okay, so what we're looking at is for the first 4, for if a high nibble is between 0 and 3 inclusive, it could be 2 or 3 bytes, could be DAA, DAS, could be AAA, AAS, or it could be one of these basic ones. Yeah, so already I think this is maybe more the conceptual path that I want to be following rather than just look at the first nibble, then look at the second nibble, and break that up into different functions doing the exact same structure. Not necessarily the ideal for performance, but I mean, that's certainly not my concern right now. I'm just thinking ahead to, like, if you wanted to do this in a bulk kind of way or as fast as possible, would it really make sense to be breaking it up in this way and sort of parsing stuff out that way? I don't know. But I think it's the most logical structure, and I bet if I were to go look at the implementation of some of the other x86 instruction decoders out there, they're doing a similar kind of breakdown. And really, I probably want to do a similar thing for these individual single byte opcodes. Instead of basic, should I call it like, what is the right term for the, like, arithmetic logic at the ALU stuff? I guess DEC and increment would be part of the ALU. And, like, I don't know, maybe, you know, maybe that sort of thing comes into play when they are trying to figure out how to encode these instructions. I would wager it doesn't really matter. You're going to do all of your decode work in, you know, on a cycle basis, 1 or more cycles. So being able to, like, figure out, oh, these go to the ALU because they follow this particular bit pattern probably just doesn't mean anything at the hardware level. I mean, maybe it did way back when, but again, increment, decrement don't follow this pattern at all. And so I don't see why it would be necessary to think of them in that way as ALU. Yeah, and like not and stuff. I don't know. I'm gonna call these, I'm gonna stick with basic for right now, I guess. And what are we gonna pass in? We've already figured out from the first opcode byte. So these are still single byte opcodes, right? Although we do need the W bit, I guess. So we should pass that in. And then, so do like, and then one past the instructions and instruction itself. Okay, so these will all need to decode stuff in the same way, and I'll have to, we'll get around to how to work out the like the special additional forms for immediate with a register in, I don't know, maybe we'll get to it in the stream. Probably not, based on the time that I have left and the fact that I'm going to start working on parsing out mod RM. Okay. So we'll say we get the mod RM byte. And we will pull out the pieces of it, I suppose. I think it was shift over 6. Yeah, then we'll get these up the top 2. That'll be mod. And oh, the compare register with memory. So this is defining the order. So wouldn't this be listed as D? Because there was also something mentioned about, oh, they said in this table they don't actually call it D. But that would be D. just these four, right? Ugh, what did I do there? There we go. Okay. So we'll get the D bit and we'll get the W bit. Ugly as hell, but whatever. Let it go for now. And we want RM and we want reg. Or yeah, I guess it is considered reg, right? They talk about it up here. What are they? Oh, maybe it was in chapter 2. We can just call it reg, I guess. Okay. And what do we want? 8 bits. Need 56, which is sorry, it is 2. No. 3. 38. God damn. Yeah. And shift that over by 3 bits. So we have I don't know why I'm testing it in Python, like that's definitely going to do the same thing. Let's go ahead and put subtrends on just in case. Okay, so we've got all the pieces of mod RM. Maybe I should take advantage of macros. Do it a little nicer. Then what do we want to do for add, for example? Yeah. Should I order it? We'll deal with that later. And okay. Do we have SIL? Ugh. Should really learn something about the x86 instruction set. Okay, so it might be possible to reference the low D word in SI or something, but not through the mod RM stuff. So I'm gonna leave it for now. Okay, so we can start to parse out the register references. So it's like switch mod So if we've got a 1-1, again ignoring these two, we have a 1-1 for mod, then we know we're dealing with two registers. What's going on here? What's the case where it doesn't return a... Everything else does break, so... Okay, I don't know. It's confusing. That should be... Oh, how do I want to go about this? Oh, this is probably the wrong way to do this, just because ugh. Why don't I make it a function instead? And ugh, how do I want to name this stuff? So I think we need to know whether we are defaulting to 16-bit addresses or operands, or whether we are defaulting to 32-bit. And then the W bit will indicate whether we are actually using a 8-bit or the whatever the default is. So 1 second. I'm gonna switch back to OBS. I haven't opened it for a little while, so or I haven't like switched to that tab for a little while, so it might crash. In which case, stream will die for a second while I start it up again. Okay, and we are back. As predicted, OBS crashed because, I don't know, I hadn't paid attention to it in too long, I guess. Doesn't like being left alone for an hour or more, it would seem. So I'm stuck on the same situation of like, I don't know. Mode is not really the name I want to use. Just gonna call it op size for operand size, but it also could be address size. And I don't know, I could, you know, in terms of representation, I'm going with an enum because it feels like the right way to go. But I could also just make it a, you know, I could do an incredibly hacky thing and make it like a single byte integer. And if the value is 16 or the value is 32, but feels too hacky even for me. So we'll do bits 16 and bits 32, I guess. Okay, so if we're trying to figure out what register we are referencing in a particular instruction from the mod RM bit, then we need to switch based on the bits. I guess. Is there a good, I'm gonna do the hackiest thing first, and then we will maybe come to a conclusion about how to do it better at some later point. So if we're in 0, that's going to be AX, A whatever. Let's say if W return AL. Let's go back to this table here. This is when W is present, which I think is the case for all of these. But I could be wrong. Yeah. Okay. So we'll do W on this just because it's apparently possible to have it without the W. So what we want to see is, yeah. It's AL when W is 0. And then CDB. We'll get to the other ones in a second. Oh, gotta do the manual name spacing of stuff because it's C. Oh, we could call this right. ACDB. God damn it. Okay. So I think that'll work. And then for 100, we've got high version of ACDB or SPBP SIDI. SP. And do that as well. Okay. I think that covers all of our cases, registers. What is this weird? I don't know why it wants to, why it's stuck on that. Okay, so if mod is 1.1, so we're back to the, let's say, add instruction. Mod is 1.1, and we have register 1, register 2. Okay. Oh, we could do it that way, I guess. It's so weird to have this bit that determines the direction just because why wouldn't you just swap them in mod RM? if you wanted them in the other direction. I don't really get it on that score. But we will do the swapping ourselves. Yeah, let's do it that way. Okay, so we'll say operand 1 is make bits to enum w of it's the reg part. Yeah. And then w and size 32 we're going to just default to, I guess. Operand 2 is going to be rm. We need to give ourselves an operand 2. Okay, and then later we'll say if d, so the d bit is set, then we just want to swap them. Whatever those operands are. And it's real questionable to do it this way. Storing the memory addresses and immediates and stuff in these operand parameters. But I think I will keep with that for right now. We're definitely not going to get to the point where we can properly parse out. Yeah, and I missed yet another bit set. Basically bit flag. So we could do that then. Let's say get rid of those and we'll change these. How is that? Oh. Did I fuck that up? Yeah, god damn it. Okay. What do I want to say here? Oops. not too long to do it all on one line, I guess. Oh, and I fucked it up on those other ones as well. Ugh. Too reliant on regular expression stuff, and I'm not making them as specific as they need to be. So many bugs in my code right now. Oh, and I'm also doing this wrong. This should be an 8, not a 7. Okay, and this needs to be a 3. So we're going to send it as a bit mask, just the low 2 bits. No, we want 3 bits. So the way that these work out is the high 5 bits ultimately determine the instruction. So like maybe we could have done the thing that I was starting with where we were parsing it out by 5 bits. So those 5 bits determine the instruction within this subcategory of instructions. Then the low 3 bits are different flags. The highest one is a flag that determines if the following data is an immediate. The middle one is the directional flag to determine which direction the operation works in terms of the operands. And then the lowest bit is the width flag, which I don't understand what that does in the context of I guess you could do it with single byte immediate, maybe? I don't know if that is explicitly mentioned. I'm going to assume that when they talk about operand sizes, that implies it also means the immediate data. So, yeah, and we have some other version here that we'll deal with in another context, I guess. So we want to pass those 3 bits, and we'll parse them out separately in the function. Yeah. Then 4. Okay, so if it's an immediate value, then oh yeah, okay. How do we want? Ugh. I've only like halfway bothered to implement the size related stuff. What would to do for that? Pretty hacky. So I think if we have an immediate value, then if W is set, it's just going to be a single byte. And so the size of our instruction is the one from the opcode and the one from the immediate. Otherwise, we're going to assume the size that we're dealing with is 32 bits. So we've got 4 bytes of operand for the immediate and then 1 byte for the opcode. So we'll return 5. And then down here, we're still working on parsing the mod RM stuff. Okay. In which case, we've dealt with this one. And we've dealt with these two. So we need to deal with these two. So this is going to require me to go more into detail again about RM specifier stuff. I think I am probably not going to start on that at this point in the stream. Been going for about 3 hours, which is the sort of time limit that I've set for myself on any given stream. It's getting kind of late. But what I will be doing is focusing on how to interpret RM and represent this stuff. And then there's going to be potentially displacement bytes. Yeah, how to combine these into a operand setting. And we'll probably need to add a third operand value for tracking the displacement, or maybe actually call it displacement or something. Like in our data structure output, we'll need to really be able to track that. So, and then we'll have reg as the other operand. Yeah, I guess I will need, maybe I'll make an operand structure, which will be, have some flags, possibly have displacement and stuff, and then we will swap those around. I don't know. Stuff to think about for the next stream, for sure. We're making some progress. The code just gets uglier and uglier. But I don't know. I feel like I have a much clearer sense of where this is going, at least for the portion of instructions that I've been looking at in this stream. Whereas on the previous stream, I felt like what I'm doing right now to parse out these couple of instructions is really not at all applicable to the reality of trying to decode everything. And I think that's been borne out on this stream, that the approach that I was taking for those single byte instructions is just not really it's sort of what I talked about when I was kind of rambling towards the beginning of the last stream, of when you set a goal that is very small and it's like way too small compared to the end goal, you don't have any of the constraints that are implicit or critical to the actual end goal. So the design that you come up with, because it doesn't have those constraints, doesn't necessarily have any reflection or relation to the design that you would need to come up with for the end goal. It's sort of trying to come up with a metaphor on the fly here, but if you were, I mean, I don't really know a lot about airplanes or anything, but I think if you look at the stuff that was tried in terms of getting people to fly, before, the Wright brothers kind of era, and the whole set of designs that followed from that, because their initial goal was so poorly stated as compared to the reality of how you might describe flying through, human powered, or not necessarily human powered, but powered flight as designed by humans. They weren't working on the same set of constraints, because they weren't even in the same ballpark of conceiving of how it could work, I guess. Like the whole flapping wings machine or whatever that what's his face? The guy. What he came up with, only in the broadest terms is that related to the idea of powered flight in the same way as the Wright brothers kind of thing. Maybe I've just made it worse with this attempt at a metaphor, but the point is, like, if I'm trying for a problem that is either too small or too far away from the actual end goal, in some capacity. It's just very different from what my actual end goal is. That doesn't count as a very good stepping stone towards that end goal. It doesn't necessarily mean that it's like the wrong thing to do. It's just sort of a low quality step. So what I did on the last stream was pretty low quality, but I understood that going in and knew that I was going to throw that code away. For the most part, I have thrown it away. There's still some remnants of it that I left in because I shifted my focus, but I will probably end up deleting them when I get around to when I finished working on this category of instructions. And it's just because I had no idea what I was going towards. I hadn't really understood the problem well enough. I guess I hadn't done enough research and certainly hadn't done enough attempting to solve a more complete version of the problem. And now that I have, I've started to come to an understanding of some of the structure that is in place in the encoding, at least as it relates to certain subsets of the instruction set. And I imagine, there's going to be exceptions and stuff, but then maybe when you get into the more advanced instructions, the SIMD stuff and all of that, because they no longer have the size constraint driving their entire focus on how to encode stuff, maybe they will have more recognizable structure in how various related instructions are encoded or something of that nature. So all this goes to show that, if you can come up with a realistic, smaller version of the problem that you are trying to solve, set that as your goal. If you can't figure out what a realistic, smaller version is, you can still put that as your goal just as a way to motivate yourself to get started. I think there's value in there when it comes to just getting started writing, in this case, writing some code. But, this sort of applies generally to any kind of project. But for a coding project, set a goal that maybe isn't, that you recognize is not very realistic as a stepping stone to get where you want to go, but is enough to get you beginning, because it's easier to continue than it is to get started. It can still be useful there, but if you can figure out what a smaller version of the problem that you really want to solve, if you can come up with a smaller version of that and it makes sense to you as a real smaller version of it and not just a completely faked, you're just sort of lying to yourself about it being a smaller version of the problem, that's a much higher quality goal to start with, I guess. Okay, enough of this rambling that I always do at the end of the stream. That's everything I'm going to get done today. I will commit this and push it up to GitHub as a, work in progress commit. I try not to do so many commits that are like the code doesn't work right now, but I'm not going to put in the time to finish the stuff that I'm currently working towards before I commit it. So I'm going to commit this broken stuff. The link to the project is in the About section, or it'll be in the description for this VOD. If you want to check it out yourself, feel free. If you know what you're doing or whatever and you want to submit a PR to fix my terrible code, I'm open to that. It's not what I had in mind, but if somebody wants to do that, I'll certainly review the PR and be open to merging it in. So in any case, thank you for watching my stream or watching the VOD if that's what you're doing. And I will be back tomorrow, Friday, June 12th. Be doing more hacking, binary exploitation stuff, really just continuing with the work of learning how to use Anger and I'm going to do my best to be prepared so that I can start working on the Anger CTF challenges on the stream rather than doing the learning part on the stream, because I don't think that was very interesting for folks yesterday. So I'm going to do everything I can to be ready to do CTF challenges tomorrow. And then again over the weekend, I will be coming in with Try Hack Me. I'll do some Try Hack Me boxes on Saturday and Sunday and see how that goes. It'll be my first shot at that, and y'all can follow along. All right, thanks everybody for watching the stream. I'm going to end it now.